Okay. So this week, we're going to cover essentially the test we're going to cover is chi-square test. But the topic is really that of what we do, our first look at what we do when our outcome variable is categorical. Everything we've done up until this point, oh, here's Mike. Everything we've done up until this point, we're assuming a numeric dependent variable or outcome variable. So last week, it was the change in VO2 max or just regular VO2 max, pre, post, things like that. Blood alcohol concentration, blood lead, intelligence test scores. And one point to make, an interesting point to make that I think shows up on a quiz somewhere, is that generally, there are many questionnaires that are validated in such a way as to enable you to create a score from them. We have a couple people from the clinical side. So Mike, I'll kind of, one thing that one might use, and this is actually used on public health screening surveys, is the GAD-7, which is a 7-question scale. It's a set of 7 questions designed to measure, to a certain extent, the level of generalized anxiety that a person is experiencing. And so even though an individual item on that scale might be considered, if we use that as an outcome, we might, and actually we're going to see for homework, one of our examples is going to be a single sort of Likert type scale item where the answers are like, bad, fair or poor, fair, good, very good, great, right? Like, so it's like, how are you feeling today? Some kind of like check-in item. A single item like that, when we have that as an outcome, it's usually not a good idea to use, say a t-test or something like that for analyzing that type of item. It's best to treat that item as an ordinal variable, which an ordinal categorical variable. So to treat it as a categorical variable, understand that there is an order of magnitude, between of the scores. So if we assign 1, 2, 3, 4, 5 to those ratings, that poor is worse than fair, so on. It's right, put them in order. But often those types of items, they don't function well in t-tests or linear regression models. So our main purpose in the lecture is going to be to deal with when we have binary categorical variables, because that's usually what we do when we have when we compute odds ratios. Oftentimes we have categorical variables with 5 categories, like I just said. And you would still use the test procedures we're using this week. However, so a single item from something like the GAD-7, this is what I love about the internet. Right, so any of these items on their own, we would consider ordinal categorical. But as you can see, there's a scoring algorithm. It's just simply the total score. So somebody circles the answers to all 7, and their score is simply just the sum of their answers, right? So if they said like 2, 1, 2, 3, 2, 2, 2, you'd add those up and you get, I don't know, was that 2, 1, so 3, 5, 8, 10, 12, 14 would be their score. If I had a bunch of, if my outcome was people's scores, a single number, that represented a score on something like this, we would treat that as numeric. So that's one thing I didn't highlight yet, but is important to note that today we will deal with variables like this, but we're singling out single ones. If I'm looking, because this is often on a questionnaire, a public health evaluation tool, or a quality measure, an after visit check-in. How is your care today? Usually those items are going to look like this, but there's only going to be one of them. And if you're just analyzing that one, and looking across, say, clinics or males and females, it's best to use the chi-square approach that I'm using today. You can then, there's a sort of a special procedure that I am trained to do to ensure that the total score is a good measure of what you're trying to measure. And then you can use, if you're using a set of items like this together, you can combine them in that way and treat that as a number like age or whatever else. So that's a whole different topic outside the scope of the course, but I did want to point that out because we'll see for homework and for practice tonight when we look at SPSS, we'll see stuff that looks like this. And so when you're dealing with a single item like this, you're going to want to analyze it the way we're going to do tonight. When you have a collection of items that you add together or combine in some other linear fashion, usually we can attack it with the t-test, or next week, linear regression, so on and so forth. So as usual, there's some content in Dr. George's little text, which is basically what we will cover in class. There's some extra stuff in there. And then this paper, which is definitely something to read, I would read, because it discusses the difference between, and we'll talk about this, but you're gonna, very, very common to see odds ratios in scientific studies in our area, but also to see risk ratios sometimes. And the two are very, very related. I'll talk about a little bit about what they both are. This goes into more depth, but the important point is that there is a monotonic relationship between the two. This graph presents it in this paper, meaning that the larger an odds ratio you have, usually the larger the risk ratio, and the lower the odds ratio, the lower the risk ratio. As you can see in this chart, there's not any straight lines on the chart, so it's not a linear relationship, and it also has to do, specifically, risk ratios vary with the percent of non-exposed folks in the population. And so we'll talk about that. There's case control studies, which are discussed in here, cannot adequately measure, or you don't get an unbiased estimate of risk or risk ratio when you do a case control study. Only a cohort study can give you that. All right, so those are the things on the docket. Let me open our slides and we can get going. So some of this stuff may be, again, familiar to you. We're going to try to tackle it with slightly more of a in-depth lens. So we'll do our, as usual, we'll do our sort of cover the conceptual stuff, and then we'll jump in and learn some SPSS. So I sort of label this week chi-square test, but really our focus this week is going to be on odds ratios and again, looking for relationships between two categorical variables. So with a t-test, what we're doing is we're looking at a relationship between a categorical grouping variable with only two categories and a numeric or continuous outcome variable. This week, we're going to focus on, again, only two variables in our analysis, but both of them are going to be categorical. And even if they're ordinal, we're basically treating them as categories, right? And so we're going to be interested in frequencies. So common variables you might see is, person has a disease versus doesn't, they're satisfied, not satisfied with care. Often, you'll see stuff like this where, maybe you've, so I work a lot with sort of survey data and also then like quality data coming from the health side. And so often there's a tendency to sort of make certain variables dichotomous. So we'll often group people like, okay, the not at all versus and a little satisfied become one group, and satisfied, very satisfied become the other group. But we're not limited to binary variables. It's just that's tends to be, first of all, our human brain likes those, and they are sort of special in healthcare, especially clinical research, anything where we're looking at a defined disease state and trying to understand why people develop that disease versus don't. One of our variables is going to be the person has it versus the person doesn't have it. So, as usual, we'll take our example from the text. So we're going to, again, dealing with some stuff that goes on in larger cities. So childhood asthma, right, is associated with poor air quality. There's all kinds of, I don't have to explain to you, things that happen to kids who experience this. So, putting that aside, Chi-Chi is now going to investigate whether there's a difference in the prevalence of asthma between boys and girls in the Philly area. And so that's what she wants to know. So essentially, what do we have? We can make this situation into a very simple set of two binary variables, right? And the way that we do this often, so this categorical data analysis is often just a lot about counting different things. So the idea here is, one way we might do this is we might just go out and take a random sample of children. So our total sample size would be fixed, say, to 200. And we would simply cross-classify these 200 children, right? They'd either be male or female, and they'd either have asthma or not. So there's essentially four, in our study, four kind of subcategories they can fall in based on that cross-classification. Right? There's some other sampling plans, but that's usually the one that we go about doing. Right? And so that's the classic cross-sectional study. We have our sample size, total sample size fixed. Right? So maybe all children aged 6 to 8 in Philadelphia are sampled at one time, and they're cross-classified. Two other ways we perform observational studies is we do a case control study. And so case control study is usually retrospective, but not always. Sometimes it's prospective. But either way, the target population is sampled in a way such that we actually sort of manipulate how many people in the sample have the disease versus don't have the disease. So our sampling plan begins with these two numbers, and then the number of people with the risk factor or what ends up being the exposure is then sort of the random variable. A third way we can look at this problem is instead of focusing on the disease variable, we focus on the risk factor. So, cohorts can also be retrospective and they can be prospective, right? They can go forward in time, backwards in time. And so either way, we're sampling not on whether or not the person has the disease. So we don't purposefully get about half of our children to have asthma and half to not, right? Case control study is mimicking what? What do you guys think?
Well, it's a controlled study, right?
Right, it's sort of mimicking a randomized controlled trial, although the outcome is the thing that we're controlling, right? Whereas the cohort study is we're looking at one group that has an exposure to the risk factor, the independent variable, and the other group is not exposed, and we either follow them forward in time to see if they develop the disease, or we look backward in time. So this is important because, again, when using risk ratios, we have to be careful with the case control design, because when we are having, again, the optimal case control design is to have a decent balance of cases and controls, right? So we don't have to have that in a cohort study. We can have like a small, number of people that are exposed and a ton of people not exposed. In a case control study, we manipulate how many cases there are. And so that ends up meaning, and we'll read more about this, that the risk ratio, which we'll define in a little bit, cannot be adequately estimated from a case control study. It's going to be biased. It's going to be wrong. All right. So from here on in, though, we can do a chi-square test. And importantly, from all three, we can construct odds ratios. So that's often why odds ratios are used so commonly, because they work in all of these situations. Okay. So we've talked about this before, about the fact that a single binary variable follows a Bernoulli distribution. And all that means is that for any particular outcome, or that any particular person, they take one of the two categories with some probability that we denote pi. And of course, we can estimate this probability, which often is called prevalence in public health, or just in any sort of disease management and disease prevention. We can estimate that actually by computing a sample mean using what we'll learn in week 7 is something called indicator or dummy coding for our variable, to code everybody with the disease to, in our data set, record a 1 as the value of their variable, and everybody else record a 0. Again, that's very common in data sets that have categorical variables to use these numeric codes. The 0-1 coding, again, is called indicator or dummy coding. And it's the way, so if you have a bunch of 0s and 1s and you compute a sample mean on those data, the sample mean is simply the fraction of 1s in your data set. So in this case, out of 20 children, 8 with asthma, 12 without, is simply just 8 out of 20, or 0.4, or 40% of the children have asthma. And if we felt this was an adequate sample size with good representation, we could use this as our estimate of the true population prevalence or proportion. So categorical outcomes are pretty much always described with proportions, sometimes with sample sizes, but usually with proportions which we turn into percentages. Depending upon what we want to do with them, sometimes we just turn it into percentage. So we would use 40%. In probability land, it's really 0.4. But you should get used to with statistics switching back and forth between proportion and percent in your head by moving the decimal point 2 places in either direction. Right. You're going to see me doing this a lot tonight because we have fruit flies for some reason. They decided to live in our house, which is upsetting because it's probably my fault. So, they're just around. I have traps, and they don't seem to want to go into the traps. They just want to fly around me. So sorry if that's ends up being distracting. Okay. So I do want to bring up, you'll see this in the text, that the generalization of the binomial distribution, which also helps us out with categorical variables, is called the multinomial distribution. And it looks just like this. It's essentially the binomial distribution for more than 2 categories. It's our probability model. We can estimate population probabilities this way. The multinomial distribution plays a very crucial role in defining the chi-square test statistic, but you don't need to memorize it. You don't need to worry about it. It's a crazy looking formula. But again, our main descriptive statistic for a categorical outcome variable is the proportion of the sample taking that value. So that's how we're going to always summarize categorical variables. In any situation in which you have a set of categories and you're using proportions and the categories are mutually exclusive, so a person can only be in one of the categories at any given time, so you can only have a disease or not have it, right? Then the proportions must always add up to 100% or sum to 1. And then, of course, like any other estimator, a sample proportion is going to converge to its population counterpart as the sample size increases. You've probably already made, if you've worked with any data, from anywhere, you've probably already made a contingency table, right? That's generally how we analyze categorical variables. We don't store or work with the probabilities. We use those. Those are nice estimates because they're relative to the total sample size. So you don't have to worry about whether, there's 20 kids that are asthmatic and are boys in this sample. Well, is that a lot or a little when you use raw numbers? If I knew that 40% of the kids were male and asthmatic or something like that, or 40% of the asthmatics were male, the percentage is a little bit easier to deal with when you're communicating effects. But for testing and even for computing odds ratios, we work with the numbers themselves, right? So a contingency table is simply just a 2-dimensional table, rows and columns, and each of the cells in the table, and we'll just go ahead and look at one, right? So here's our 200 children. Each cell on the inside of the table represents the number of participants that fell in that cross classification, right? So we have 57 males who have asthma, 42 males that don't, 50 females that have asthma, and 51 females that don't. Right, so we call these the cell counts, cells, just like in Excel. And then on the margins of the table, we have the marginal counts or marginal totals, right? So we read off the rows or the columns. So if we had 57 and 92 together, overall, marginalizing over or ignoring whether the person has asthma or not, there were 99 males in our sample. Same thing here, females is 101. We can also do that with the columns, so ignoring gender and just looking at whether a kid had asthma or not. 107 children in our sample had asthma, 93 didn't. So these tables are useful for lots of different reasons, but importantly, you can compute pieces of information that are helpful for analysis and that really answer and give you the answer to a particular hypothesis test, which is the variable represented by the columns statistically related to or dependent on the variable represented by the variable represented by the rows, is that statistically related to, or is it dependent on or with the variable represented by the columns? In deriving the test, statisticians just use lots of different symbols for the things that we find in the columns. Right? So because of the way that the overall sample size is fixed, we can actually turn each one of the cell counts into a probability or a proportion. These are joint probabilities, right? So the probability or proportion of male cases is 57 over 200. And so this notation, I and J, representing row and column. So pi ij, we have 4 of those. Pi 1, which is the estimate of probability for what's represented by first row, first column, which is male cases. So that would be 57 over 200. Pi 1, 2, so row number is 1, column number is 2, 42 over 200. That would give us, again, a population estimate for male controls, and we can proceed accordingly. Then we have the marginal row and column probabilities that we can also compute by simply, again, taking the marginal totals and dividing by 200. So, often it's the case when you have a sample that when you look at the proportion of males and females, it's close to 50%, not always. But if you just go out into the world, and then you'll see a different split for other things. So point is that the way that we approach looking at the relationship between categorical variables is in dealing with these different totals, the cell totals, the marginal totals, and their probabilities. Right? So for example, if you wanted to do all the math out, it's right here. Okay? So if we put it all out, put it all together, right, we've got 49.5% boys, a little over half, so 53.5% asthma cases. If we wanted to look at the proportion of boys with asthma, it's 28.5% of the total are boys with asthma. There's 2 different ways you can sort of look at that. However, we can do something important, right? If you think back to what I talked about, and I went over it briefly, but in week 2, when we dealt with some of the rules of probability, we saw that, or I discussed that, if 2 random variables are statistically independent, then this relationship will hold. So if being male and having asthma are statistically independent, so they're not related. And so being male doesn't have any bearing on or give us any information about whether you have asthma or not, then this equation should hold, right? That, which is as follows, that the probability of being a male asthma sufferer should be equal to, in the population, the product of the probability of being male, the marginal probability of being male, times the marginal probability of the case, of being a case. So we now, from our data set, have all this information to do this test, right? To answer the question, is asthma independent from gender in this sample? And we will see that in a little bit, once we get there, figure out what we test and how we communicate it, that this becomes our null hypothesis for our chi-square test, right? Is variable X independent from variable Y, or vice versa? And as far as the test is concerned, this is true of correlations we'll deal with next week. It almost doesn't matter which is which, because this is not a causal statement. So we could flip-flop it and we'd have the same results. But research design often dictates what would be the causal factor and what would be the outcome. And so again, that's true most of the time, that causal evidence is outside the scope of our statistical practice. We have to have extra information to know about that. Okay? So qualitatively, we can judge whether or not this equation holds by looking at the information we have. So this notation is just, again, the probability of being a male and having asthma, which we have right here, right? It's the 57 folks in our study that are male and have asthma divided by the total. That gives us our population estimate of 2.285, so 28.5%. Now, here's the important part. If it were true, if our null hypothesis was true, that asthma was independent of gender, then if we multiplied these two numbers together, which represent the marginal probability of being male and the marginal probability of the case, we should get this number, 0.285. So down here, we can see that it works by doing it in fraction land and also in decimals, that we do not get the same number. Similarly, if we did it by count, if we computed something called the expected count, which is basically the proportion turned into a count, we would get 52.9, so about 53 male asthmatics, which we can see is different from the 57 that we observed. And so that's another piece that becomes important, right? Is that we're going to utilize in our test an expected value for these cell counts and the observed values. And basically, right, what the expected values represent is they're what we should expect if the null hypothesis is true. If the two variables were statistically independent, what should our table look like? Does it look like the table we have? And if it does, right, if our expected counts look just like our observed counts, then the null hypothesis is probably true, and we would go with it. Right? If, however, there is a discrepancy between our observed data and what we would expect, if this statistical independence held, then that would be evidence against independence. And so the alternative would be, oh, there must be some relationship. Okay? So that's what we're after. And it's much easier to understand and do when we have this very simple, the simplest of contingency tables, the 2x2 table. The twos represent that, right? That the first two represents the fact that the first category has two levels, or the first variable has two categories, and the other two represents that. So we'll see later when we do our examples that we can have 2 by k. Usually we use k, the letter k, denote the number of categories. So it's not uncommon to see, 3 by 5 table, so on and so forth. But this 2 by 2 table has plays a very special role, especially in epidemiology and the development of this test and so on and so forth. Okay, so qualitatively, we know that there is a discrepancy here. But now what do we do? How do we actually quantify this discrepancy? So I'm going to take us on a little bit of a detour. We're going to talk first about risk ratios. So one thing we can do is to compute the proportion of boys with asthma and the proportion of girls with asthma and put them in a ratio. The reason we use ratios, so to this point, we've used differences. So last week, the t-test is all about, is the mean level of something in this group different in some way than the mean level in this other group? Differences in proportions are not always the best way to test research questions about those proportions. And so instead, we might compute something called the risk ratio, which has a null hypothesis that the proportion of say disease state in one category is the same as the other, right? So pi 1 over pi 2 would be, proportion of males with asthma over females with asthma. And the null hypothesis, when a ratio is equal to 1, how do we get a ratio to equal 1? What must be the case about these two numbers for, if we divide them into one another, that we get 1?
They'd have to be equal.
Mm-hmm. They'd have to be equal, right? So, so that's one way to do it. We could construct a test about the risk ratio. And again, we use our estimates of probability of the disease or whatever we're looking for, some characteristic. We'd use the two separate groups. So this would be, again, group 1, measure of asthma prevalence for males versus females. So this sounds great because, again, it's not too different, and we can use pretty straightforwardly use what's in the contingencies table to do that. And again, what does a ratio give you? It gives you sort of how many times larger is the denominator or is the numerator compared to the denominator. So when a risk ratio is 1, it means that it's not any number times 1 is that same number, right? As the risk ratio grows, so it gets greater than 1, it means that the numerator is larger than the denominator. As it dips underneath 1.0, 0.75, going that direction, it means that the denominator is the larger number. So I want you to keep that in mind, because that is also true of odds ratios. As I said, they're not linearly related. They're not the same exact thing, but they generally carry the same information, and they have they behave the same way. Okay. So back to the issue with case control studies. So the first reason a risk ratio is limited is you can't compute it from a case control study. The reason is because we've already chosen the proportion of the sample that has the disease. And so these are biased estimates of probabilities. And then the second thing is that the distribution of the risk ratio is very complex. It doesn't help us out for hypothesis testing. But there is something related called an odds ratio that just so happens to be, you can validly compute it from a case control study. And its distribution is related to the distribution of the cell counts, which makes it really, really nice. So when you're testing independence in your table, you're essentially testing an odds ratio. The downside of odds ratios and odds is that odds are weird. Probabilities we can kind of understand as proportion or percent, but what are odds? Now, this issue with understanding odds is compounded by the fact that now that legal betting is everywhere, the way that odds are represented in betting is different than the way we usually represent them in medical and health research. For some reason, they make them different. And, I'm a statistician and I can't seem to understand why the money line looks the way that it does and whatever. They just represent them really in a different way. But for our version, for our purposes, the odds of an event, and so let's call that event I, are the probability that I happens divided by the probability that it doesn't. So this really only works if we have a Bernoulli distribution, if we have a binary variable. So the odds of something happening versus not happening, or you can do it without, for a horse race or something, but you've got to kind of dichotomize as you go. But just like risk, an odds greater than 1 indicates that the probability on top is larger, so that the probability that the event happens is larger than it not happening. And odds less than 1 means the probability of event happening is less than it doesn't happen. Right? So odds greater than 1 means it's likely the event's going to occur. Odds less than 1, likely that it won't occur. Odds equal to 1, 50-50 chance. We're not going to be totally interested in odds alone. You can think of odds as likelihood of occurring, right? When we talk about odds ratios, we'll use this percent difference or percent interpretation. I think that's more helpful when we will put odds and ratios with other odds. But again, greater odds for an event. So if the odds is a large number greater than 1, the event is likely to happen, much more likely to happen than not happen. If odds are less than 1, the event is much less likely to happen than not happen. Okay. Finally, we get to what we're interested in, which is the odds ratio, okay? Which is the ratio of odds of an event for 2 different categories. Okay? So on the top, right? So again, this now requires us to define a dependent variable and an independent variable, an outcome and a risk factor, say. So again, our example as we've been going forward is the risk factor is the child's gender and the outcome is whether or not they have asthma, right? So what our odds ratio is is it's the odds of having asthma for one group, we'll call it asthma for one group, we'll call it the male group, divided by the odds of having asthma for the other group. So it's a ratio of odds. When we put odds in a ratio, the interpretation is very similar to odds by themselves, right? But now we're looking at essentially how much larger or smaller the odds of something happening in one group or situation are compared to the other group or situation in the denominator. So if an odds ratio is greater than 1, that means that the odds of the event happening in the group represented by the numerator are larger than the odds of the event happening for the group represented by the denominator. Okay? So again, if we had odds of asthma for males on top and odds for asthma for females on the bottom, the odds ratio would tell us how many times larger or smaller the odds of asthma for males were compared to females. Also, like the risk ratio, an odds ratio of 1.0 means equal odds. That the odds of being asthmatic if you're a male are the same as if you're female. Okay. So if the odds ratio is equal to 1, it's pretty much identical, but not exactly the same as the two probabilities being equal, as the risk ratio being equal. But it represents a similar enough case that this works for us. So this is why odds ratios have become so prevalent in this type of work, because they work across any type of sampling situation that we find ourselves in. The cohort study, the sort of cross-sectional, grab everything at once study, just sample a bunch of people and see what happens, and the case control study. Odds ratios will work, will give us some important information. And it turns out, and I'll sort of skip over the math for this, it turns out that we can test an odds ratio by using a test on the contingency table itself. We can't do that with the risk ratio. So SPSS is going to compute odds ratios for you, and importantly, it's going to compute a confidence interval for the odds ratio, which is very, very important, just like it is for anything else. But it's helpful to see how it's done. In a 2x2 table, the odds ratio is pretty easy to compute. It turns out if you take the formulas for probabilities and then turn them into odds and turn them into odds ratios and cancel all of the terms, you end up with a pretty simple formula, which simply is just a function of the cell counts. Now, the one thing that's important is that this odds ratio is directional. It represents a specific way that the table is set up. Right? So the way this table is set up, and using this formula for odds ratio, it's going to give you the odds of male asthma divided by female. So the numerator is going to be males, the denominator is going to be female. On the next page, we'll see what happens if we want to do it the other way. Okay? So again, it turns out that Chi-Chi's study was a case control study, so we can't use a risk ratio. And anyway, most people use odds ratios and they're easy to communicate. So using the table of previous data, let's compute odds ratio. Now, if we go back to statistical independence, right? we're sort of at the point where if these two things were statistically independent, then their odds should be equal. And so we should get an odds ratio of 1.0. So we're going to compute the odds ratio and see is it 1.0. So you can see right here that it's not. So how do we compute this? It's sort of an easy thing to think about as you kind of make an X. You start with the top left cell, and this only works for 2x2 tables. You can't do this with a more than 2 columns. You can do it though by altering a table, right? So if you had, and we'll see, when we get to SPSS, we'll have an example in which we have, 4 or 5 columns. You can make that into a 2x2 table and compute an odds ratio that way if you want to. Usually people do that where they compare, if it makes sense to combine categories, which is usually the case for ordinal variables and not necessarily for categorical variables. Anywho, you simply multiply these two numbers on a diagonal together, and that represents the numerator, the odds of being an asthma case and being male. And then you do the same way on the other diagonal. And so we get 1.3843. What does that mean? Well, there's 2 ways to interpret that. That means that the odds of being asthmatic and being male are 1.3843 times larger than the odds of being asthmatic if you're female. So odds ratio as a plain number gives us how many times greater the odds are for whatever it is we're looking for. So in this case, for having asthma, the odds of having asthma, how much greater are they for the group represented by the numerator compared to the denominator? So again, here we see that the group represented by the numerator, those are the boys, that compared to the girls, the boys have an odds of asthma that are 1.3843 times greater than the girl. So this on its own represents what we call an effect size in the literature, because you can generally compare odds ratios across studies as being big or small for a particular study topic. However, that's not like the most straightforward interpretation, right? So instead, another way to, and so that's perfectly fine. So if I asked you to interpret an odds ratio and you saw it was 1.38, and you said, well, that just means that the odds of the disease are 1.38 times greater in the one group than the other, that's perfectly acceptable, correct answer. Sometimes it's a little bit more meaningful or whatever to use the bottom interpretation. We call this the percent change format. So instead of saying how many times greater the odds are in one group versus the other, we say how much of a percent difference is there? Right, so to compute it, you simply take your odds ratio, subtract 1 from it, and multiply by 100%. And when you do that, if you do this often, you'll figure out a heuristic for doing this in your head. So, here I'm just dropping the 1 and moving the decimal point over 2 points to 38.43%. If we have an odds ratio that's less than 1, it's a little bit different. We'll see it on the next slide. But how would I describe this? I would say that the odds, there's a sort of a 38.43% difference Or if I went from being male to female, I would see, or if I went from, if you change from being male to female, sorry, from female to male, you'd see a 38.343% increase in the odds, or difference in the odds. So an odds ratio can be interpreted in terms of a percent change or percent difference between the groups. And that's a difference in odds. Now, again, what's odds, right? Odds are still a little abstract, but again, we think of odds as likelihood. They're not probabilities, but you can think of them as the greater the odds, the more likely this event is to happen to a particular group. So the greater the odds of asthma for males, the more likely it is to happen to males than not happen. When we put them in a ratio, it's giving us sort of a ratio of that likelihood of happening, right? And so when this ratio is greater than 1, it means the event is much more likely to happen to the first group than it is to happen to the second group. And we can quantify that. We can say, oh, it's 1.3843 times greater. The odds are greater in one group versus the other, or as a percent difference. What happens though if you were speaking, say, to a public health organization, looking to try to specifically protect, inner city young girls or something like that? You might want to make females the group that you were, sort of talking about, putting them in the numerator. So how do we do that? Well, we have to reconstruct our table. And this is true in SPSS, okay? But the odds ratios are dependent on the way the rows are set up. Just the rows, not the column. Well, the columns too, but we generally need to have the event, right? So being a case, having asthma, be in the first column no matter what. And then you flip-flop the rows and we change the odds ratio. The result of that is simply just taking the reciprocal of the odds ratio. So you can go ahead and compute this, or you can see that for the male interpretation, we've got 57 times 51 over 50 times 42. Here we've got 50 times 42 over 57 times 51. We've just flipped the ratio upside down, okay? Which is equivalent to just doing 1 divided by this odds ratio. Okay, so let's say SPSS, your data are set up such that it's computed the odds ratio in one direction, but you want it in the other direction. You can try this with your calculator now. I'll bring mine out, right? So I want everybody to try this just so they see it for themselves, right? So if you on your calculator type 1 divided by 1.3843, you're going to get the number on the next slide. You're going to get 0.7224. So you don't, you're not going to compute these by hand anyway. So you don't have to actually flip the rows upside down. The result of flipping the rows upside down is that the ratio has a new meaning. It just flip-flopped, okay? So importantly though, let's see what this means, okay? Now that females are represented by the numerator, the ratio still tells us how many times greater the numerator is than the denominator. But that number is less than 1. It actually means the numerator isn't larger than the denominator. It's smaller than the denominator, right? So that in this case, the odds of having asthma, if you're female, are 0.7224 times the odds of having asthma if you're male, which means there's 75% of what the odds are for male, right? They're less than 100%. a less confusing way to kind of report that or think about it is to use that percent change notation again. And here, whenever the odds ratio is less than 1, we're going to get a negative percent. That's good. That tells us something, right? So as a percent change, right, odds ratio of now the newly computed one with male is the comparison group, females on the top. 0.7224 minus 1 times 100% is negative 27.76. Okay? So again, when I go from, so that basically the difference between female and male odds, it's a 27.76% difference. The negative sign lets us know that females have the lower odds compared to male. 27.76% lower. Again, this is telling us the odds of having asthma versus not having it is 27.76% lower in girls, the numerator, than it is for boys. Whereas over here, we would say, right, the odds of having asthma versus not having it are 38.43% greater in males, the numerator, versus females. Okay? Same information, just presented in a different way. All right. Let's see. Does anybody need a break or should we keep going? This is sort of a natural place in the topic to take a break, but I can keep going. What do we think? Any? All right, I'll tell you what. Let's
keep
go
going.
through.
You can keep going for me.
Yeah. Yeah, let's do a couple more slides, and then if we feel like we need to take a break before SPSS, we definitely do that. But if we need to do it a little bit earlier, we'll do that too. Okay. So just to summarize, to this point, we've kind of quantified the effect of interest, right? So if we go all the way back for a minute to here, right? The fact that qualitatively, right, we don't have statistical independence. We've now sort of quantified the amount of, or the relationship between the two variables, right? We've shown that the relationship is such that males tend to have greater odds of asthma than females, right? But statistically, we'd also like to have some evidence that comes from hypothesis testing. So again, we can construct a null, we have a working null hypothesis, but it would be good to see if we can get ourselves into the land of p-values, and also what this does for us is if we know the sampling distribution of the odds ratio and the test, we can construct confidence intervals for it, which is always good. Again, confidence intervals help us to communicate the uncertainty in our estimates, and also aid inference in a different way. So the other thing is odds ratios are generally limited to binary categorical variables, and a 2x2 table, except for logistic regression will break out of that. So using odds ratios by themselves doesn't do it for us, because again, we're often going to have situations in which we have many categories, more than 2. Okay? So if instead of the odds ratio, or in addition to it, we want to do this test of statistical independence, which by the way is also more difficult in the way that we did it before, just by looking at the table qualitatively, there is a test for it. Right? So we can formally test for statistical independence between 2 categorical variables. And it's the same conclusion, or it's the same hypothesis, right? the working null hypothesis would be, is this one variable statistically, or this one variable is statistically unrelated to the other, which again means that we don't get any information about the second variable from knowledge of the first. That would be what statistical independence generally means. So if we know that two things are statistically related, again, we can do some science, we can do some predictions, so on and so forth. So this test also works for a 2x2 table. And again, it turns out, and I won't present this, and I don't even know if it's in the text, it's in other texts, that formally performing this test, which we will call the chi-square test for independence, will also, in a 2x2 table, test the significance of the odds ratio. So we can use this test if each individual is independently jointly classified on each variable. So the individuals need to be independent from one another, and they have to be able to be jointly classified in a mutually exclusive way. So what does that mean? That means if you're in this study of gender and asthma prevalence, you can only be in one and only one of the cells, right? So you have to be only classified in one way. And again, we can use this in many different designs. In this way, we use frequency data, so we don't even have to use the probabilities. Even though we're going to construct, our null hypothesis is going to be about probabilities, we can actually just use the frequency data. So the null hypothesis for this test in notation is simply that formula for statistical independence, which is that the joint probability of the two variables is equal to the product of the marginal probabilities. And the alternative hypothesis is that that's not true. So that's what this states. If you, and this is from the text that you can see, right, what these plus signs mean. Those are the marginals. So again, if we're looking at male and female, right, we're looking at the relationship between asthma and so gender and asthma. We'd look at a joint probability, say of being male and having asthma, and then examine the product of the marginals and see if they're the same. The null hypothesis is true, they're the same. If it's not true, they're different. So what's true of the probabilities are true of the counts. This is also another way to say that the cell counts are basically equal to the product of the marginal counts in a particular way. So this is just derived from the product rule for independent events of probability. So the way that we compute the test statistic is for each cell, we compute this ratio. So in words, the ratio is the observed count in that cell minus what we expect it to be squared, divided by the expected count. In symbols, we use Nij for the observed count and mu ij for the expected count. Now, expected count is easily computed. We already did it. The expected count, once again, if we look at our table, you see our marginal counts. the expected count, the expected number of male asthmatics is computed as 52.965. What we're doing is we're taking the marginal total number of males, which we see to be 99, and multiplying it by the marginal total number of asthma cases, and then divide that by the overall total of 200, and we get an expected count. So you can do that for every single cell. So basically a chi-square test just relies on these numbers. Can be computed very easily just based on those numbers. And again, you're not going to have to compute it, but it's actually not too difficult. So, right, in this case, for that first cell, we'd have the 57 minus 52 point whatever squared divided by the 52 point whatever squared. So we use the Greek letter chi or chi, but most people say chi. Square is part of the symbol. Again, the n's here represent the observed frequency of the observed count, and mu is the expected frequency or expected count. We do this for each cell on our table. So if we have a 2x2 table, we do this 4 times, and we add all those numbers together. So we're going to get a ratio, right, observed minus expected squared over expected, get a number for each of our 4 cells. If there is a large difference between observed and expected, going back to that original example, that means that statistical independence is probably violated, right? So if we get a large discrepancy, the chi-square test is basically giving us a measure of discrepancy between the actual data we have and what would be the case if the null hypothesis was true. Right? So the magnitude of the number, which is a sum of those individual discrepancies, is related to rejecting the null hypothesis. So the null hypothesis should not be rejected when these discrepancies are small. When these discrepancies are large, we reject the null hypothesis. So indeed, this is a one-tailed test, if we put it in p-value language, and a large chi-square value is going to be associated with rejecting the null hypothesis. Large chi-square will go with small p. So here's some more information about the chi-square distribution itself. Again, you can see in the book, there's a derivation of it, basically as a sort of a squared version of the normal distribution. It's not important that you know that. Actually, sorry, t distribution. And because it's related to the t distribution, it does have degrees of freedom. It's positively skewed usually. And each chi-square distribution does have a different degrees of freedom, which can be computed from the contingency table as the number of rows minus 1 times the number of columns minus 1. Now, this will always be equal to 1 then for a 2x2 table. 2 rows minus 1 is 1. 1 column, or 2 columns minus 1 is 1. 1 times 1 is 1. So the degrees of freedom for a chi-square test of independence usually are relatively small. Other situations where chi-square degrees of freedom can be very large. Right? So here's just a few examples. Right? Degrees of freedom equal to 1, the chi-square distribution is really funny looking. It sort of has a limited peak at 0. And so the sort of tail probability is very large. And we're going to evaluate our p-value, we'll see on the next slide, is related to how much of the distribution. So we'll get a chi-square value, we plot it on the x-axis, and figure out, well, how much of the distribution is to the right of that chi-square value. That's going to be our p-value. So for example, if we were doing a chi-square test with degrees of freedom of 3, and we were testing at alpha 0.05, our chi-square test statistic would have to be at least 7.81. If it was 7.81 on the dot, our p-value would be 0.05 on the dot. As it gets larger, p is going to drop 0.04, 0.03, 0.02, all the way out. As chi-square gets smaller, right? And again, the smaller the chi-square value, the less discrepancy there is between the observed data and our null hypothesis model. So in this way, we're really dealing with compatibility in the way that Sander Greenland talks about it in his paper that you may or may not have read. So it's always a one-tailed p-value. It's not a directional, it's a non-directional test. So how do we compute it? Again, you're not going to have to do this by hand, but I think it's helpful to see. One thing that you are going to need to do is make sure, one very important assumption of the chi-square test is that there are no, so over here we see the expected cell frequencies, the expected counts, which are computed using that formula. So for each cell, you multiply the row total by the column total, divide by the total. And so 90 times 107 over 200 is this one. 90 times 93 over 200 is this one. 101 times 107 over 200 is 54.035, so on and so forth. These numbers all must be greater than or equal to 5, or else the assumptions of the chi-square test fail, and so the p-value won't be accurate. So SPSS does this for you in the background, computes the expected frequencies, and obviously we feed it the observed frequencies. And then it does all this math for us. So for each cell, it takes observed, we subtract expected, square it, divide by expected. So that's just represented observed minus expected squared over expected for the first cell. Then we move to the second cell, observed 42 minus 46 squared over 46. Third cell, and it doesn't matter what order we go, just as long as we match the observed and expected frequencies, right? Because this is a sum, so we can move this, right? We can do it out of order, but we have to make sure that we're using the correct expected and observed frequencies. So we do all this math. So we get numbers, 4 numbers, we add them together, we get 1.3090. That turns out to be a relatively small chi-square value. If we used a table or we used a computer, we'd find that the tail probability is 0.2526. So if alpha is 0.05, this p-value is higher. It doesn't meet our criteria. So this is akin to sort of being over here, whereas this would be our reject region. This is the accept region. Our test result in this case is in the accept region, right? So this is important, right? Because our odds ratio is not equal to 1.0. And the observed and expected frequencies are not identical in any of the cells. But remember, we're dealing with sampling error, right? So what this computation does for us is it says, well, relative to sampling error, do we have, or in the context of sampling error, do we have evidence to overturn the null hypothesis? And because our chi-square is small, p is larger than our alpha of 0.05, we say we don't have enough evidence. Okay? So how would we write this up? We'd say from a sample of Philadelphia children, and now we're going to use the second version of the girls as the focal group. Right? The girls have a slightly reduced odds of having asthma compared to boys. And so we have the odds ratio from the female perspective, which shows that they're a little bit less. And then I'm not going to show you how to compute the confidence interval because it's sort of annoying for odds. You have to transfer to log odds and then transfer back, and it's a real pain in the butt. One thing to note, though, check out this confidence interval. Does this confidence interval for the odds ratio include inside the range? Does it include 1.0? I often say it straddles 1.0, right? Our confidence interval goes from 0.414 all the way up to 1.262. Remember, best way to think about a confidence interval is it's a range of plausible values for the statistic of interest, in this case, the odds ratio, the true odds ratio in the population. 1.0, an odds ratio of 1.0 represents our null hypothesis, that there's no difference in the odds, or there's no relationship between males and between asthma and gender. That number is in our confidence interval. And so again, so just another example of that we can, in fact, use confidence intervals for hypothesis testing. This will always agree with our p-value. So we see that our p-value says that our evidence was not conclusive. Right? Evidence against the null is not conclusive. And indeed, our odds ratio confidence interval shows that even with this amount of discrepancy and with a point estimate for the odds ratio, indicating that girls have reduced odds, we don't have enough evidence that that's really true. The null hypothesis is still plausible. All right. Good. Okay, so that's we made it through the slides. We're going to spend more time tonight on SPSS because it's a little bit more involved with this. Before I do that, I think the important thing, there's kind of two important concepts this week. First is the odds ratio. And so you want to get a good understanding of that. And I think, again, the way Dr. George writes about it, and we've just gone through the examples from the text to make it, give you another example of it. I think he does a nice job. And then that risk ratio versus odds ratio papers is going to give you a little bit more background on it. Okay. It's an important statistic in its own right, just because it's just they're bandied about all the time. All health and medical folks, it's always odds ratios. And then the second thing is now we've introduced a new sampling distribution. Okay. So we've added a third sampling distribution, which is you can think of as a place we get p-values. We now have a third one, the chi-square distribution, which is a very important distribution in probability theory and sampling theory. It is often a distribution that you see it in the context of categorical data analysis, and it pops up other places too. Pops up sometimes with other tests that are related to z-scores and normal theory and things like that too. And with coupled with last week. So we have chi-square. We've learned about the t distribution as well. We're going to use that throughout the course. Chi-square we'll use when we get back to this content in the context of regression. And the normal distribution is always there hanging out in the background because it's sort of a lot of things are based on it. T distribution is related to it, it's based on it. Chi-square distribution is related to it as well. Everything else is pretty much the same, right? So again, we have a new test statistic, a chi-square value that we want to be large. If we want to overturn the null hypothesis, chi-square has got to be large, p needs to be small, just like before. Well, good. Why don't we take 10 minutes, break, come back, and we'll navigate SPSS. Sound good? All right, see you in 10. So on Canvas, I added this today, week 5 practice. So we've got practice problems and then 2 data sets. We're going to start with the psych data set, and then we'll use the aspirin data. So let me share my version of the data. So the psych data is data that Heather is processing. So she's got patient records for the psychiatry department at the hospital for review of how psychiatrists tend to prescribe drugs to patients based on disorder. 276 patients. We have the psychiatric disorder they were diagnosed and whether or not they were prescribed drugs. So basically kind of go through all of these things with the exception of the null and alternative hypotheses can be and will be computed using SPSS, including the contingency table. Now, data like this come in 2 forms. Usually you've got the full data set, right? So if I was Heather or you were Heather, you would have pulled records for all of these people and probably created, a row for each of the 276 patients. You'd have a column with their diagnosis, and you'd have a column which said yes or no, they were prescribed drugs. In the olden times, you wouldn't process the data directly that way. You'd have to kind of put it in contingency cell format first. And so just sort of for legacy purposes, we're going to take a look at how that's done, in SPSS. So if you look at the files that we have, they look a little bit different than what we're used to. So we have, instead of a data set with the number of rows equal to the number of participants, what we have is sort of a data set where the number of rows is equal to the number of cells, right? So this is a 2x5 table or a 5x2 table. And we can actually see it in the PDF. If you scroll to the end, you'll see it. We'll see it in a second. We can see it here, right? So we have diagnosis, schizophrenia, affective disorder, neurosis, personality disorder, special symptoms. And then we have that repeated again because we've got the yeses and the nos. And then we have a count of how many there were in each cross classification. Now, in order to analyze this in SPSS, we have to take an additional step. Right? So we've got to go to the data menu. This is the data menu. And all the way down the bottom, we see weight cases. It's very important. So you've got to do this first. You click on weight cases. And then the only thing in there is going to be count. And you want to click the toggle for weight cases and move count over there and press OK. Because what that's going to do is now SPSS is going to interpret these data correctly. It's now going to interpret these as counts rather than, and as individuals, rather than, as it is now, it just looks like it's 10 numbers. So you have to do that first. That's data, weight cases, reset it, right? It'll look like this, do not weight cases. We're going to weight the cases by count. So the files for homework, you'll have to do this too. You wouldn't have to do this if you had a big data set. And again, you had 276 people and you had a column that said diagnosis and it was one of these 5 things in the column. And then you had another column that said drugs prescribed. You could do the same analysis that way. All right, so we've done that part. We've now made sure that when we do our analysis of, and again, the question, right? So if we go back to our null hypothesis, what would our null hypothesis be here? I mean, you can kind of just say it in terms of what it is, as it says there. Right? The null hypothesis is that diagnosis and whether or not drugs were prescribed is independent. That's our null hypothesis. Now in symbols, you might see it laid out this way, which basically just says it statistically, right? That for all I and j, so for all rows and columns, the cell count or the cell probability is equal to the product of the marginals, right? That each one is, for each cell, whether or not the person was prescribed drugs is independent of their diagnosis. So this just says it's in symbols. Okay. So now this information, the cell counts, is already in SPSS. We've already got that here, but it looks funny. And we don't have the totals, and we don't have the expected counts. Now you don't always have to get the expected counts. SPSS is going to look for you and make sure that the assumptions of the test are okay. But it's a good idea to get them, and sometimes you're going to be asked for them. So how we actually analyze this data is we go to analyze, and we're going to use, there's 2 places to do chi-square tests. One of them is under non-parametric tests as a legacy dialog for chi-square. We're not going to do that. Our version is actually in descriptive statistics. And we're going to use something called crosstabs, cross-tabulation. Okay. So descriptive statistics crosstabs, click on it. And we're going to move the variables that we need to the rows and the column boxes. Now, because we've weighted the cases, we don't have to do anything with count. We just leave that where it is. So for this analysis, it doesn't so much matter what the row and column is, but we're going to follow what we see on the paper. So we'll put diagnosis in the column, and drugs prescribed is going to be the rows. Now we have a few options we can choose. If we first look at statistics, we have to ask for chi-square. So by default, this is just going to give us a cross tabulation. So we go into statistics and we click chi-square. Because we're not dealing with a 2x2 table, we're not going to get an odds ratio. We could ask for it, but I'll wait until the next one. So for tables that are larger than 2x2, the only thing you need to ask for here is chi-square, and that's under the statistics box. In the cells box, you can ask for a bunch of stuff. Right now, we're just going to get observed and expected. So observed is by default, Then we click for expected. We could also get the percentages if we want to. That makes the table really cluttered, so I'm not going to do that. And those are the only basic things we need for chi-square, is to ask for the test, and then we don't even need the expected frequencies, but we're going to ask for them just to inspect them. Right? So I click OK. And as you can see, SPSS has done what it was supposed to do. It's turned the data into, right, here are the regular counts, so that'll match what we see, although it's flip-flopped. Instead of yes, no, it's no, yes. And so we can see that for affective disorders, we have basically differing numbers. The column totals show us how many patients are diagnosed the different ways. So, for example, there's 113 schizophrenics. There's only 14 people with affective disorder. But as we can see, the splits is a little bit more even. So 94 not prescribed any drugs, 182 prescribed drugs. You can also see our expected counts. Now there's an issue here, so we'll get to that in a minute. We can see down here in the test, chi-square test, right, that we have a couple of different numbers. That's going to be true. You might see a bunch of different numbers here. We're always going to read off the Pearson chi-square. Pearson chi-square. And so in this case, it's 84.18 or 19, really 188. Degrees of freedom of 4. And here's our p-value. It's very, very, very small, less than 0.001. So we've just tested our null hypothesis. What should be our conclusion here? Is our data consistent with the null hypothesis, which would be that whether or not drugs are prescribed to a patient is independent of the disorder that they have? Does this tell us, what does this tell us about that? So again, this is a p-value, it's very small. In previous weeks, what did a small p-value mean? What conclusion would we draw about the null hypothesis, or about evidence for an effect, if you want to go that way?
So there was no evidence to reject the null hypothesis.
Well, we have evidence, right? We have a lot, actually, we have a lot. So small p means we can reject. Large chi-square, small p, reject the null hypothesis.
Right? Okay.
If we had a large p, small chi-square, we wouldn't have evidence to reject. Now it's harder to see here, right? Because it's like, what's going on? The way to eyeball it is, for each cell, it looks like, so if I'm looking at the count versus expected, the numbers are, especially for schizophrenia, very, very different. For the no's, and not so much for the yeses, but definitely for the no's. So it looks like many fewer schizophrenics than expected were not prescribed drugs. Now there's one problem here, and you can read off what it says. So 2 cells have expected count less than 5. The minimum expected count is 4.43. So this is bad. So we can see this expected cell count for the expected number of folks with an affective disorder, but who are not prescribed drugs, is 4.8. And same thing for here. the expected number of folks with special symptomology who weren't prescribed drugs is 4.4. We don't want any cells. So this, for us to be okay in interpreting this result cleanly, this should say 0 cells have expected count less than 5. And you will see that. We'll see that in a different example. So this is an example of a table that's larger than 2 by 2, but is the assumptions of the test are not fully met here because we've got 2 cells. We only need 1 and we're not in a good place, right? So we've got, in this case, we have 1 or more, right? We've got 2 cells in our table with expected counts. It's not the observed counts. It's okay that we have a 0 and a 2. That's fine. It's the expected counts need to be greater than or equal to 5. And again, when they're not, so in this case, basically the p-value can't be trusted. So we have some evidence, we've got, if we didn't worry about that, we've actually got quite a bit of evidence that there's a relationship between whether or not you're prescribed a drug and what disorder you have. However, we have to caution that these results might not be valid because we have failed to meet this assumption. Some things that you can do about that is, here's where you can sort of start to combine categories. So you might, for example, affective disorder, you might combine that with the others, or in some cases you make it binary. You might make, schizophrenia versus everything else. And that will clear up the test. You can then still test the relationship, but now you've sort of just made the data a little bit more coarse. So you can help yourself out.
Can I ask a question?
Yeah, sure.
I'm just confused about what we're supposed to do with the chi-square value. Like, what makes it, like, obviously 84 is a high number, but when is it high enough to say that that is
Right.
significant or
So this, this is why SPSS can sometimes be annoying. So what we've got in this table is we've got the chi-square value, the degrees of freedom, and this is the p-value. So whenever in SPSS you see less than 0.001, that means that p is very, very small. For whatever reason, p is not labeled as p in SPSS. It's labeled as significance, or in this case, it says asymptotic significance, which is a technical term. But it's still a p-value. So again, just like before, we'll look at this number in the significance column. It's our p-value, and we'll compare that to alpha. So it's confusing because it looks a little bit different. And now it says asymptotic significance, which is, I'm not going to explain what that is.
but with the chi-square number, like that value, is that just for reporting or?
Yeah, it's the test statistic. It's like a t value.
Okay.
It's like t. It doesn't have any intrinsic meaning. Kind of rule of thumb is that the expected value, if the null hypothesis is true for chi-square, is relatively equal to the degrees of freedom of the distribution. So in this case, if the null hypothesis is true, we would see chi-squares around 4, because that's what the degrees of freedom are. Our chi-square is 84. It's much larger. Right? That, back to the lecture, large chi-square means large discrepancies between observed and expected. So evidence against statistical independence or statistical dependence. That's a great question. Yeah, just like so it's weird, right? Because T and Z, they were symmetrical. So you're moving into the tails, you're moving away from, right, the hypothesized mean. Here with chi-square, the larger it gets, it's quantifying discrepancy. So a large chi-square means a large discrepancy between, in general, your data and the model that you're testing. We're testing a model. It's a null hypothesis model. It's a model of the world in which these two variables are not related. Right? The chi-square number is a measure of distance between those two models. So the larger the chi-square, the larger the distance or discrepancy between the null hypothesis world and the world that we sampled our data from. Does that make more sense? Great. That's a great question. Thank you for asking.
So for this, can I just say there is sufficient evidence to reject the null hypothesis?
Yep. So let's take a look at how we might write this up. We'll also revisit some of the things that we see on the practice problem. So we got our contingency table. It's a little cluttered. Let me show you what it will look like. Let me show you what it looks like without the clutter. Oops, wrong data set. It looks a lot nicer when we don't ask for the expected counts, but everything else is the same. Here's our contingency table, our null hypothesis. Note that so here's our expected counts, which again we got in a rather cluttered table. Just this is them pulled out. Note that the marginal totals are identical between expected and observed. Indeed, the marginal totals is how we compute the expected counts. And so that'll always be the same. And so that pop, so we have to ask for expected. The observed counts will come. Here we're actually, so for practice, you could do this. You don't have to do this for homework. You're calculating what are called the residuals. So each part of the chi-square computation is a residual. It's telling you a squared relative distance, how much discrepancy is there. And so you see for the schizophrenics, so this, we can ask for these. I forgot about that. I don't ask you for homework, but whoops. Just show you if you wanted to know. They're in here, residuals. So you can see that they're the same, right? There's only one set of residuals, and so those are the raw differences between observed and expected. That's all they are. So perform the appropriate test so we can see. All right, we use our little symbol chi-square. As with t, we use a subscript for degrees of freedom. Also denote that there's 4. Why do we do that? If someone was reading and they didn't see the table, they didn't see that there were 2 rows and 5 columns, this clues us into that fact, or that's the chi-square distribution that we're using. Again, 84.188, we just read off. And the p-value that goes with it, it's actually not even shown to you exactly what it is. So you can just report it exactly as you see it here, matching SPSS, that p is just less than 0.001. So not only is it less than 0.5, but if we had used an alpha of 0.001, it would be less than that too. Are the assumptions for the test met? Why or why not? So no, right? Now there's other assumptions that we're going to assume are met. Whenever I ask about this with chi-square, it's really we're asking about the expected count. So we saw that, right? There were two cells, the affective disorder and special symptoms without drugs, those folks. And we can see them right here, right? No drugs, affective disorders, no drugs, special symptoms. We have expected counts less than 5. Okay, so no good. It didn't meet the assumptions of the test. However, if we were to interpret the results, we would say this way, right? We'd say the data from the patients showed an association between the diagnosis received and the psychiatrist's decision. Give our chi-square. Although the small number of affective disorder and special symptom cases makes the results somewhat unreliable. So this is just a statement in plain language saying the assumptions of the test weren't met. So there may be some issues with these values here. But Stephanie, yeah, in general, you'd say there's an association, there's statistical evidence for association. We could say with, statistical blah, blah, blah. I don't mind if you use the term significance, that's fine. Statistically significant association.
How do I write that X in 2/4?
Yeah, you do it in whatever way you want. You can type X, so it's actually a chi, it's a Greek letter, just like alpha. But you can type an X and a 2, or it doesn't matter. An easier way probably to do this. So I do like the subscript degrees of freedom, but the way I learned in APA and psychology format is to put the degrees of freedom in parentheses. Sometimes it's a little bit easier. So for the chi-square symbol, just do your best. You can do an X squared or even X with a 2 next to it. That's fine for me. In a research paper, technically, and I have to do this all the time, and it's a pain, but I do it. You go in to Microsoft Word symbol selection, find the lowercase chi, insert it, superscript squared, and then I copy and paste it through the paper. The hidden things that statisticians have to do.
Thanks.
That and data cleaning is a good deal of our job. Copying and pasting Greek letters, and then also italicizing the letter P, and data cleaning. That's most of a statistician's job. So this is a good example. Oh, so let's talk about this part too. Okay, so it's the last part. And this is just using your eyes, right? This is all we have to do to actually, once we do this part, right, so say there's an association, then we just go look with our eyes at the table. Right? So, in general, we observed that far more patients with schizophrenia and far fewer patients with personality disorders were prescribed drugs than if the choice was independent of diagnosis. Okay, so that's right. We're looking here at the discrepancies, right? Or the differences between observed and expected. So kind of we're reporting the two greatest discrepancies, right? That for the schizophrenics, we saw that there were way fewer. It's kind of backwards the way this discrepancy is. It's better in the SPSS. We can see it the right direction here, right? So there were way fewer schizophrenics that were not prescribed drugs than would be expected. And there were way more folks with personality disorders that were not prescribed drugs than would be expected. So all we're doing is you could go through each cell and say that, or at least each column and say, oh, for affective disorders, whatever. But we're kind of focusing on the two biggest discrepancies, which were for personality disorders and schizophrenia. So that would be the way, sort of the qualitative takeaway, kind of akin to, oh, there was a big difference between these two groups' means. Here we're looking at the discrepancies between observed and expected. All right. So now we'll do a quick odds ratio example and then call it a night. Just back here. So back to Lou again. We'll hear a lot about Lou and his study of myocardial infarctions and heart attacks. So a very large trial, patients. I think this is real data. It's a famous data set. 22,000 patients at low to moderate risk for MIs were recruited in a trial where they were told to take a daily pill, which happened to be aspirin, and half were randomized to. So told to take a pill, half randomized aspirin, the other half given placebo. Patients were then followed for 2 years. So this is a prospective cohort study, really randomized control trial, prospective trial. So again, it's asking you for basically the same stuff. You can compute risk. We're not going to do that. We're going to focus on the odds ratio and then the chi-square test. And so I'll just kind of show you a few things, right? So our contingency table, the risks are basically just, sort of what's the risk of myocardial infarction? Well, we can just do the various, so the total risk is 1.3% of the patients experienced an MI, 1.7% were placebo versus the 94% aspirin. And so we're basically trying to see is there a difference? Are these related? Of course, the risk ratio is just those two numbers, probability of myocardial infarction if you were taking aspirin divided by if you were taking placebo. And so the risk ratio is less than 1, and which suggests that aspirin has a protective effect. But is this a case control study? Right? It's not. It's a randomized control trial, but still we might want to get an odds ratio. So now you can get this stuff from SPSS. It can compute risk for you, and and I'll show you, but you can also compute these for yourself. The important thing is computing odds ratio. So we have it here, okay, but I'm going to show you how to compute it. And then of course the null hypothesis. In this case, interesting. So it's really still a test of independence, but we're actually testing the proportions, whether the proportions are equal. Proportion of basically we're testing for equal risk. Are these two proportions the same versus different? So now there is a test for difference of proportions. It's just a little bit different, but we're going to use the chi-square test for it. So we'll go to that data set. And we're going to do the same thing with it. Just make sure that we're weighting the cases. So go back to data, 8 cases by count. Again, we see our contingency table here in a sort of a strange fashion. So now I'm just going to go ahead and do the same thing as I did before. Go to crosstabs. Now what I want to do is put MI in the row, treatment. No, I think I want to do that backwards. I always forget. Sorry, yeah, treatment is the rows, outcome is the columns. you get the same result, but it's better to do it this way. You won't get the same odds ratio. The question is, how do we get an odds ratio? We go into statistics and we ask for chi-square. Down here, we see a couple of options. One of them is risk. Okay, click on that. Now, because this is going to give us risk ratios. Now, if those are inappropriate, we're going to look at the odds ratio. This gives us both. So it's kind of annoying. Again, SPSS is labeling things awkwardly. But to get odds ratios, we have to click the risk box. So by default, neither of those are checked, right? So I have to go in and click chi-square and risk. Continue. Chi-square and risk. Then in cells, we'll go ahead and ask for expected, and let's get those residuals too. And we're good. So we've got our observed counts for aspirin and placebo. We've got our expected counts. We've got our residuals. We've got a few different options now. But again, we're going to look at Pearson chi-square. And there's even more p-values to choose from, although they're blank, right? So again, we're going to have, just as before, it's just a bigger table. We'll discuss Fisher's exact test in a later week. That's why we have the extra columns. So we see our chi-square is 25.014, degrees of freedom of 1, p-value of less than 0.05, it's less than 0.001. So this would be evidence against the null, evidence for an association, or for a difference in risk between the difference in risk of heart attack between aspirin and placebo group. Whichever way you want to phrase it, all of those things are equivalent in terms of what the chi-square can tell you. Importantly, and you could see this in the table, but it also tells you it right here, right? 0 cells have expected count less than 5. The minimum expected count is 146. It's greater than 5. So that's great. So these data do not violate the assumptions of the test. So this is the same as before. Our new piece of information is we get risk. Right? So we've got risk for the two yes and no, which isn't actually giving us any information that's helpful, because what we want is risk for aspirin versus placebo. And anyway, we're going to just ignore that. We want the odds ratio, which we have right here. Okay? Now notice, okay, it tells you very clearly that this odds ratio has the aspirin group in the numerator and placebo in the denominator, just in the way the table looks. So this is showing us that the odds of MI that makes no sense. The odds of MI are greater for aspirin than placebo, which doesn't make any sense. This makes me think something's not something's not labeled correctly, because the counts are correct there. It's very strange. That's weird. I wonder why I did that. That's the reciprocal. Did I do something wrong? I'm just going to reset this.
That's weird. I don't know why it did that. Okay, so it's actually the reciprocal. Huh. Oh, I see why it did that. Okay. Right. So this is a tricky data set. Right. What it gives us is this is actually the odds of not having a heart attack. So the odds of no. Why? Because no is in the first column. Okay? So the event of interest is the first column. And that's how SPSS computes it. Right? So what we have to do is, so that's cool. So we have the groups correct, right? Because we're going to want to compare aspirin to placebo, but the event is flip-flopped. So this is, as we would expect it to be, with the odds of not having a heart attack, if you're given aspirin, are greater than placebo. But the question was about what's the ratio of having a heart attack? What's the risk of having a heart attack, not the risk of not having? So how do we get that? We can still, I believe, take the reciprocal, or we move and compute it. Yeah, okay. So we would take the reciprocal of everything, and that flips us around. And actually, we see it down here, right? For MI equals, yes, we see our, so if you've got your columns flipped around, the row down the bottom is going to give you the correct. So our correct odds ratio for risk of MI, or odds ratio of MI, is 0.550. So it's, the odds are about half for aspirin versus placebo. And then we have our confidence interval. Right. I always forget to practice. Plus, I get these from Dr. George because they're great problems, and they've always got the practice problems always have little complexities in them. Right. So now you could have computed the 0.55 OR, and then what he's showing you here is you're flipping the first line gives you a confidence interval, and you're taking the reciprocal, but it's also in the third line of the table there. So we have our test result. And then here's how we would describe this. We did a RCT. We observed an association between whether or not patients were assigned to aspirin and whether they experienced heart attack. And by the way, this chi-square will be the same no matter how you flip-flop the table. It's the odds ratio that depends on having the table in a particular way. And so we estimated that the daily aspirin reduced risk of an MI by 44.99%. So how do we get that? So from that third line of the table, we're taking the reciprocal of the 1.8. We get 0.5501, subtract 1 from that, multiply by 100%. Right? We get negative 44.99%. So, right, the group on the top had lower odds of heart attack. So note here that we're giving the percent change as our point estimate, but then the confidence interval will always just give as the odds ratio. The homework problems aren't as complicated. It will be straightforward. The data are set up the way that they should be. So one thing to take away from here is, in order for SPSS to show the correct odds ratio in the first row, your event of interest has to be in the first column of your data set. It's not, and so you can look down at the bottom to find out the answer for when it is. So I believe SPSS does it alphabetically. Yeah. So if you want to, so SPSS automatically codes or orders everything alphabetically. So if you want to hijack that, right? So if I wanted to flip-flop it, if I wanted to force the yes to be in the first column and the N to be in the second column, probably best thing to do would to be create a new variable with 1 standing in for yes and 2 standing in for N for no. You could even you could do it like, allow me to do 2, 1, yeah. Sorry, 1, Y, 2, no. 1, Y, 2, no. Go with the string. So what am I doing here? Now, since I put numbers in there, it should do it correctly. Let's test it. Oh, oops. One more time. The wrong thing. There we go. And so there we get our correct estimates. Note the chi-square is the same, right? So now I've moved the yeses to this column. How did I do that? SPSS sorts strings alphabetically, but if you have a number, it puts the number first. Okay, so that's it for this week. Any other questions here? So next week is asynchronous. I will be in Baltimore, and I don't know what